Hi, this is video 2 once again for the book C++ Premier Plus. Um, to just let you guys know, I actually own um, the the paperback version of this book, and Safari gave me you get a free 45-day trial. That's how I'm being able to access the book and play with and kind of mark notes and things like that. Okay, so let's start with chapter 3. So what is this chapter about? So okay, in general, when you talk about a variable, there are three things that are important. First is where the information is stored, what value is kept there, and what kind of information is stored, right? So when you do int brain count is equal to 5, it means, okay, where the address of the brain count variable, that means where is this value 5 stored, what is the value stored in that address, that is 5 in this case, and what type of value that is, like is this an int or a float or a character or something like that, because that will basically tell the compiler that as to how many bytes do you want to read to extract the value of the variable stored at that location. Okay, so yeah, so we basically, I just explained you that. Just some variable names, you can use all these kinds of variable names. Try not to use an underscore something, because it's reserved, and so is with something that starts with 2 underscore. It should always start with a character, so something that starts with a digit is not allowed, and underscore is allowed, but hyphens aren't. Okay, so now let's look at the data types. So this is important. So there typically these different data types: short, int, long, and long. But life is not that simple. What that means is the implementation as to how many bytes that is dependent on the particular data type is the number of bytes that are dependent on a particular data type is implementation dependent. What that means is a particular compiler / platform can be different, can do it differently than, let's say it will be different on Windows versus Microsoft versus Unix. So there's those technicalities that you have to deal with, and we'll look at it later as to how, what's the right way to do these things. But this is what the specifications says. A short integer should be at least 16 bits wide, an int should be at least as big as short, a long should be at least 32 big and at least as big as int, a long should be at least 64, and things like that, right? So these are some of these are the specifications that when okay, this is how you should, this is how your implementation, this is what your implementation should adhere to. Now here's the important thing. Yeah, bit we all understand in zeros and ones, and byte is typically, we say that okay, a byte is 8 bits. Is that true? Well, that's not really true. It usually means 8-bit of memory, but it's not always the case, and we look at some other things later as to where, so why is that not the case. So let's look at this. Okay, this is just this point just highlights as to how big long and long are. So what it means is unsigned long can't hold the Earth's population or the number of stars in the galaxy, but long can. You just don't want to use long because you'll end up always, because you'll end up wasting memory. So you have to be conscious about what you need, and then how much and hence which type should you use. Byte is the unit, etc. Okay, some implementation. Okay, so we spoke about that. Okay, but here's the deal. International programming can require much larger character sets such as Unicode. So some implementation may use a 16-bit byte, right? Or even a 32-bit byte. Some use the term octet to denote a 8-bit byte. So it really depends, what a byte may be. That is kind of important here. And some implementations give you the choice to handle length. Okay, these are different variables. The size of, so this is important, the size of operator returns the size in bytes of a particular type or variable. Byte is implementation dependent, so 2-bit int could be 16 bits on one system and 32 on another. This is important, and you can look at the limits.h header file to find out specific details about your implementation. And it's here in this particular case it is using some, it's getting all this int limits.h or c limits, and it's getting all these values and just printing the values. In this case, int is 4 bytes, short is 2 bytes, long is 4, and long is 8, so on and so forth. And this is how you would do. You can do size of int or size of n short. You can do both int or the variable name. Okay, so this is, and the C limits typically contains lines similar to the following: define in max to be this value. Okay, so that's, it's kind of hard coded right there. And so here we see that you are using the define constraint, the define directive, but what you will see later is that you can use const, which is a much better way to do it in C++, because as you can see here in define, you don't see the data type for int max, but in const you can do that and other things as well. So these are various ways you can initialize things. You can do this is equal to something, but you can also do this is the alternative C++ syntax, that is in brackets and stuff like that, and so on and so forth. You can also define multiple things. Okay, so typical overflow behavior. Let's say you start with 0 plus etc. Then this is the reset point, and it shifts to negative. And for unsigned integer, what basically happens is it just continues increasing, right? So when you kind of, let's say you're going in the anti-clockwise direction, yes, you are going in the anti-clockwise direction. After this particular point, you still continue increasing. You no longer have a negative. And 0 is considered positive. Hence, you can see it's 0 to something odd number, and then it is 67 to this one even number, right? So the range is the same, but you want to give the same numbers for positive and negative, so as to speak, correct? Okay. And 0 is the reset point. Okay, so portability, use long for big integers, because as we have spoken about it, that int may be 4 bytes on newer machines, but maybe 2 bytes on the older system. So you want to hence use long, because long is at least 4 bytes on the older machine as well. Now, okay, so what is this? Okay, so these are various representations that we can have. So we can have 3 different representations typically: decimal, that is what we usually do; hexadecimal, that is to the base 16; and octal, that is to the base 8. Now what is the idea here? If the first range is between 1 to 9, it is 10, that's etc. If the first digit is 0 and the second digit is in the number 1 to 7, then the number is octal. You can see 0, 4, 2. And how do you do this? It's 0 raised to something plus, actually you should go this way: 2 into 8 raised to 0 plus 4 into 8 raised to 1 plus 0 into 8 raised to 2. So 4 into 8 raised to 1 is 4 times 8, 32, plus 2 should be 34, which you can see that's what it means to be decimal. The same thing you can do for here as well. When you see a 0x, or is this hexadecimal, and in this case it's 2 into 16 raised to 0 plus 4 into 16 raised to 1, and 4 into 16 is 64 plus 2 should be 66, which is the case here. Make sense? Okay. And A to F represents 10 to 15 for the hexadecimal stuff. Okay. So that I just kind of quickly explain how do you convert particular number to a different one. Okay, some more notes. Okay, okay. Cout.put. The cout.put function is your first example of an important object-oriented programming concept, a member function. So as we know that a class defines how do you represent data and how to manipulate it, a member function belongs to a class and describes a method for manipulating the class data. The OStream class, for example, has a put method that is designed to output characters. You can use a member function only with a particular object of that class, such as the cout in this case. To use the class member function with an object such as cout, use the period to combine the object with the function. This is called as the membership operator. The notation cout.put means to use the member function put with the class out. You learn about greater detail when you see object and classes, but and just to get some more, just so that we see what does this cout.put mean. So you can do this, and you can also do this. Okay, you can do whatever you following repeated characters as desired. So yeah, so what it meant is that so a statement like the following will print the ASCII code for dollar instead of simply displaying this. It will actually print the ASCII code, and hence you want to do this put business. Okay, makes sense. Okay, some character codes and things like that. When you have the choice between using a numeric escape sequence or a symbolic escape sequence, such as this versus this, use the symbolic escape sequence, correct? The numeric representation is tied to a particular code such as ASCII, while the symbolic code works with all codes and is more readable, right? You want to use /b instead of using this, slash 0x8. You don't want to do that. You want to use the /b version, preferably. Okay, so I want to take a quick digression. I want to quickly digress and talk a little bit about white charts and things like that, and encodings. I just want to give a spiel about it, and both the 16 and 32-bit characters as well. So initially, when programming started, and it started with the English-speaking countries, with the United States in particular, and there were only so many characters that somebody needed. So they said that okay, 8 bits are probably enough to represent all characters, and that's what was the start. But then they realized that you need more. 8 is not enough. You need more things, and then C++ introduced what is called as wide-char, which is 16 bits. They said that okay, that's what it is needed. Now, in C++, there are 2 explicit ones, even because it turns out that even wide-char wasn't enough. So there are 16 and 32_t. So these are 2 new characters. So now let's just talk about. So these are what are Unicode systems and things like that. Now let's talk about what is encoding. Now let's say there is a 32-bit character. Let's say everything is encoded in. Let's say everything are 32-bit characters, right? Now you may have different encodings. What it means is UTF-8, UTF-16 or UTF-32. You can have different encodings. And what this encoding means is how do you store these characters into a file. What that means is just think about it. That let's say you have defined this as char 32T. But then all your characters are only ASCII. In that case, if you save them in using the encoding as 32, then UTF-32, it's a waste of space, right? Because you're just kind of wasting space. So what you may want to do is use UTF-8. In that case, it will use the minimum number of 8 bits as as desired, when it is correct, and will increase the bits as needed. Okay, so the idea is that the encoding specifies how are you saving these characters in the file, and then you want to make sure that if you have written something in UTF-8, you also read something in UTF-8, otherwise it will kind of get screwed up, correct? But your information is not getting lost, right? Your information getting preserved. You just want to know the encoding that is reading when you're reading and writing to the file. So that's what's important. Okay, bool type is something that C++ added, and in case we know about that, it's true and false. I'm not worried about it. Okay, so I should maybe have spent one last point there. That so it still allows that you can say 0 is false. Now here's interesting. 0 is false and everything else is true. As you can remember, in the case of the int, when you are returning from a program, 0 means correct execution and everything else means error, but that is not the case here. Okay, const, we already spoke about it. This is the keyword const. Int months is equal to 12, so you can now use months, and months can't be changed anymore. So you should try to use this const type name is equal to value instead of the hash define. So that's what you should try to do. Okay. floating point numbers. The second method for representing floating point numbers called as the E-notation. Okay, so let's look at, okay, what is another method for representing floating point numbers. If you say that 3.45 e raised to 6, it means it's 3.45 multiplied by 10 to the power 6. So e raised to 6 is 10 to the power 6. That's pretty much what it is. The 6 is called as the exponent and 3.45 is called as the mantissa. Okay, so that's what it means. So let's look at some of these things here. So this is the notation. You can use plus or minus. Decimal point is optional, obviously. And then you can use e or small e. Plus or minus can be omitted. And so it's raised to and then raised to something, right? So it's 10 raised to minus 31 plus 16 and stuff like that. Now let's look at, so this is now let's understand. So we spoke about encodings, etc. in the previous page. So let's talk about precision a little bit more. Okay, so float is typically 32 bits and double is 64 bits and long double is something like that. Now as you know that float can store a lot more than long, correct? But it has the same 32 bits. What that means is that it is not going to be that precise enough. That's the basic idea here. And so what we talk about is significant digits. So significant figures are what is important, and what it means is the following are the number of significant digits in these particular types. So double, you start with float, it is 6. Double, it increases to 15, and long double it increases to 18. And number of bits, and these are the number of bits that are used to represent the mantissa. And once again, you can see it's going on, it's increasing. Mantissa, as you remember, if you think about the exponential notation, you know what is the number of bits. And these are the following are the maximum number of exponent values. Okay, so these are not the bits, these are exponent values, because as you can imagine, this is 10 raised to something, correct? So so as you can see, that number is huge when you look at long double and things like that. So let's look at this. So what that means is float. So so once again, the precision is you start with float, then with double. So you start with FD. Okay, so always remember that it's the other way around. It's float and then double and then long double. So what that means is float is going to be more precise than double. Is that correct? So float, not really, because double holds, I'm sorry, I said it wrong. Since you start with float, and float has 32 and double has 64 bits, then double will be more precise. So it will be good to 16 places and good up to 15 places, right? So what that means is, so let's look at this. So and million is 1.8. Okay, so this is again float. So tub is this, a million tubs is this. So when you multiply A by B, because it's going to be only it is only going to be precise for this much for the float value. But the double, when you look at double, you can see that the precision it is a lot more precise, correct? That's the idea here. And there is some see out tops, trailing zeros and things like that. The floating point, over integers, they can represent values between integers. Second, because it's much larger. On the other hand, floating point operations are usually slightly slower, and they can lose precision. So that is important. They're slower and they can lose precision. So let's try to understand that, because that is the key. You can't lose precision when in integers, but with floating points you can. And you see an example here. A is 2.34 e raised to 22, and B is A plus 1, correct? And when you do B minus A, you expect to see 1, but what you actually see is 0. Okay, so that's kind of the interesting thing here. And why is that the case? Is the problem is represents a number with 23 digits to the left of the decimal, correct? It's 23 digits to the rest, 10 raised to something 22, correct? So 23 digits to the rest of the decimal. By adding 1, you are attempting to add 1 to the 23rd digit of the number, but float can represent only the first 6 or 7 digits, so trying to change the 23rd digit has no effect on the value. Okay, so this is what is most important. So trying to take the 23rd, why is that the case? So because in a 20 for 6 or 7, so as you can imagine here, it is 2 raised to there are 32 bits. So let's just talk through it. There are 32 there are 30, so let's look at this. Let's, we had learned the precision here. Number of significant digits for float is 6, and the total number of bits is 32, correct? And number of bits to express mantissa is 24, correct? That is the left side, and so on and so forth. Okay, so just remember this particular thing, that okay, where did I go? That you want to be careful about. You just want to be aware about this, and so if you do these things, it will not even affect these things. So you may want to use a double or things like that. Okay, arithmetic operators. Okay, so once again, adding 11 to this should yield 61 point, but the output reports this. This is not an arithmetic problem, it's a problem with the limited capacity of float to represent significant figures. Remember, C++ guarantees only 6 significant figures for the float. If you round this to 6 figures, you get this, which is the correct value to the guaranteed precision. If you need greater accuracy, you should use double or long number. Okay, so that's the basic idea. Just remember that thing, and you'll be fine. Okay. Okay, both the division and the multiplication operator have the same precedence, so it doesn't tell what to do. So it will just do left to right associativity. I always try to just put brackets so that it's very obvious what I need to do, so that I don't confuse the reader. Okay, so when you do this, it will int operation, long operation, double operation, and float. So it's double by default, and float if you explicitly put an F, because the compiler knows that double is better. That's kind of the idea here. It's optimized for that. These are once again the same thing. The long value such as this to a float, it will result in loss of precision. It can have 6 significant figures. The value will be rounded up to this number. Some may pose difficulties here. So this is, once again, I would suggest for you to really read a little bit more, even on the side, about precision and loss of precision when you cast things, and what should you use. Be very careful of that, especially if you're doing some banking applications or things like that of that sort. Bigger number floating point, okay, such as double to float. Okay, when you are moving conversion, bigger number floating point type to smaller numbers such as double to float, lot of precision, value might be out of range, result is undefined. Floating point type to integer, once again, original may be out of range, and bigger to a smaller integer type. So you can, it can be both out of range, and you can kind of, it's undefined at that point of time if you do something like that. So auto declaration. So this is going to come up throughout this book. So I'll just spend some time talking about it. In C++, you probably know var. I don't know if there is something like that in Java. I would assume there is something like that. What that means is that you don't have to explicitly specify the data type of the variable, and the compiler will determine the data type from the declaration, and then use that as the data type of the value of the variable. What that means is, if it is determined it is x as a double, you can't just change x to an array going forward. That will break. So that's the idea here. That's chapter 3. Let's look at chapter 4 now. And now we are going to go with compound types. So we learned simple data types here, and we're now looking at compound types in this chapter. Arrays. How do you define an array in C or C++? You say type name int, my array of what is the size 50 or something like that. Okay, and this is for example, here's an example: float loans 20. Okay, uh, okay, so creating an array, we all know about arrays. I'm kind of going to skip over it. You can initialize the array in the where you declare it, and all these things are okay. This is not okay because you have to explicitly say int, and this is also not okay. Now we look at arrays and pointers and understand this particular last statement a little bit better as to why this is not okay later. You can also do something like this. In this case, all the elements are set to 0, and you don't have to explicitly specify the number of elements. You can just say, hey, this is things is an array of short, and just give the number of all the elements, and the compiler will count it for you. And what you can also do is, if it is an array, and only if it is an array, you can do size of things to size of short, and size of things will be the total size of all the elements of the array, and size of short is the size of individual element in the array. So hence, when you do size of things by size of short, you will get the total number of elements in the array. Strings, you can define it as a character array. This is not a string. You have to explicitly null terminate it with 0. That is important if you are doing it this way. You can also do something like this. In this case, the null termination is understood, and the length of the string, okay, this is important. The length of the string is only the length of the non-null character. It basically is, let's say the length of the string is 1, 2. Let's look at bird. The length of bird is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so it's 10. But you can see it's 11. Why is 11? Because you want to give 1 for the /null at /0 at the end. So although when you look at length, it will be 10, but the space required will be 10 plus 1. So there is some quirkiness of C, the way it was designed. But as you can see, if you do it here, then let the compiler count, and once again the 0, it will automatically add it, the 0 at the end. If you just define it as bozo and 8, then the compiler will put a bunch of /0s at the end, the null character at the end automatically, and if you do the length, you will get 4 as the length. Okay. Yeah, once again, while determining, this is very important. Don't forget to do that. Okay, the various ways. Size of gives the size of the entire array. String length, okay, not the size, etc. Just not null characters. I already spoke about it. Okay, I've spoken about all these things. These are just I am kind of glancing over this page, but these are just various ways to get input an array, input string, and things like that. And I think we all know it, so it's kind of just glossed over it a little bit, but you can figure that out. Yeah, so this is the important thing. The problem when Cin reads the year. Okay, so let's look at this. So this is the code. So Cin year, and what is the address /n, and it gets the address. It leaves the new line generated by the enter key in the input queue. The get line reads the new line as an empty line, and that kind of will assign a null value to the address array. Is to discard the new line, and you can discard it by just doing a cin.get. Okay, so that's important. String class. So later on with C++, there was an explicit string class that was introduced. Okay, thankfully. As you can see here, now instead of doing this, this is how you can define these strings, right? String S1, str2 is Panther, and you can just define this and not have to worry about that. You can still use the string same as an array. What that means is the string can be, you can say 2, you can do these various things, and it will go to the second index of the array. So it kind of just works. You can use the array notation. You can declare as a simpler variable, not as an array. So this is really neat. Okay, you can definitely do this. You cannot do this, right? You cannot do character 1 is equal to character 2. You cannot point these two arrays at each other. They mean nothing. You cannot do array assignments, but you can do this. when you do this, what is going to happen is the content of str2 is going to be copied on the content of str1. Okay, so we are going to get a copy. Remember that it is similar to a variable. You're going to get a copy. If you do int b is equal to c, then the content of c is going to be copied to b. The same thing happens when you do str1 is equal to str2. It's not a pointer, it's a variable. And this is just something that, kind of this example describes that for you, that okay, when you get a different you get a different string when you do plus, etc. Okay, program sentence which is larger than this. Okay, yeah, so this is something interesting. The first is when you do this, okay, character, so you define char as 20, and when you try to do string length of char, you get 27. What's going on here? Well, the interesting thing is it's uninitialized, so it's undefined, so there's no idea what it contains. It's just going to try to find a /0 at the end, and wherever it finds a /0, it will say, okay, that's the length of the character array. So you don't want to do things like that. Okay, you want to maybe initialize them to 0 or something, to null characters or something like that. But I think using friend function, okay, we'll talk about friend functions later. Okay, raw strings. So this is also very neat. This is introduced in C++11. This is the latest standard. Similar to, as we know, that if you have to do this slash, if you want to just have quotes. Now the quotes is a terminating quote. It can be a terminating quote, but you actually want a quote in your string. So you can do this clunky slash quote business. Or you can just say that, hey, this is R, and use this as the raw string, and then you can do a lot of things inside it. You see, you just have a slash n, you have a slash, you have quotes within it, and that's it. You can just put that as is. And if you already, now the interesting thing is that let's say if you want the combination, if you actually want to also use the close brackets and this in a string, then you need to do this. You need to use these three things, okay, that this and this have been replaced with this. So this is the important thing. Okay, so this is how this is the notion of raw string. So you can do something like that. Okay, I think I may have glossed over it, but then since we were talking about strings and this letter R, it came to my notice that if you are using wide character, you have to specify L. It means it tells the C++ compiler that, hey, use Unicode for it, and then you can use different for char 32T and char 16T, and I think it will also come later. So it's not that we'll miss it. Structure. So structures were the constructs that were defined before classes, and the idea is that you define the structure, and it has properties, and these are all public by default, and this is kind of a variable. A structure is a variable. So think of it, when you send a structure to a function, you are sending a copy to the structure and things like that. So that's the basic idea. I think if you know classes, you already know structures, so I'm not going to spend too much time about it. The good thing about it is that if you want to use the structure, you can just directly use inflatable. You don't have to use the keyword struct. As you know, in C you have to do that. So I will always, now that I think about it, maybe we should always use C++ because it's much more easy. Okay, so the keyword struct is defined in C. It's not required in C++. You can just use inflatable when set. So that's pretty neat, right? So try to use C++ syntax. That's more closer to Java and C#. Okay, so you can define a struct inline. You can initialize it in inline, doing something like that. And why you can do is, how the compiler knows is that it stores the variables in order. So they're contiguous blocks in memory. That's why it will assign this to the first member variable, and the 0, 1 to the second member variable, and so on and so forth. It can obviously use a string as well. You can define variables in line like this. Yeah, sure, you can do all these various funky things if you want to. You can obviously have arrays of structures, very simple. Nothing great about them. And you can also use bit fills in structure. Okay, union. So what is the difference between union and structure? Is a data format that can hold different types of data, but only one type at a time. Okay, I honestly don't know why I have never used the union, just to let you guys know. But yeah, so one for all, you can use either an int or a long or a double in this particular union. So once you do this, you can't do this going forward. Okay, so that's the idea. Enumerations, once again we know about this enum name, and give all the enumerations of part of the enum. Then you can do spectrum is a type, and you can do spectrum, is band, and you can do blue, band is equal to blue, and stuff like that. So you can directly, the interesting thing is you can directly use blue. As you know, in C# at least, you have to do spectrum dot blue, but here you can just do band is equal to blue. Yeah. Setting, and you can also set values for here, which is kind of neat. More than one enumerator with the same value, you can do 0. So 0 is and null are 0, and 1 and 1 and numero in 1. Pointers. Okay, so we now, so I am going to, maybe I will quickly go over some important parts of the pointer, but I will actually point you to another source of lectures, which I think you should just you should just listen to, because those are really very good pointer lectures. So let me just quickly glance over this, but that's is not the right. I don't think so. This does justice to pointers as those lectures do. Okay, so but at least this is a good summary, so I think it will at least be helpful. Now, int star pointer update. So what does this mean? It says that p updates is points to int. That's what it means, right? Is a pointer to int, or more concisely, int pointer. So p is a pointer, and star p is an int and not a pointer, right? So that's kind of the idea. This is the example about what this means. When you say int dux is equal to 12, dux is this guy. But when you say int asterisk bird dog is equal to address of dogs, in the bird dog you actually store the address of ducks, which is 100, and then when you point to it, it points to ducks. So that's kind of what happens. So you can do, the star doesn't really matter. You can do it this way or this way, but many they like int star pointer, just to make sure that pointer is a PTR is a pointer to int. Okay. You can't do this, because if you do this, then unfortunately the pointer attaches to p1, and p2 just becomes a type of point of int and not int pointer. So you want to explicitly say that. Always initialize a pointer to a definite and complete address before you apply the dereferencing. Yes, otherwise it's some garbage, and who knows what's going to happen when you try to dereference it. Yes, instead of this you can do new, type name is new pointer. So let's look at this. The syntax is new int allocates some space, and then you can say 101. In that case, it will copy this 101 to that address location. And whatever you do new, you do delete. Okay, that's the idea. You should delete, or it's safe to apply delete to a null pointer. And you can also do this with arrays. So let's look at that. Now it's pointer psum is a pointer to an array, and then you can do delete psum, and you need to use this brackets when you do that. So that's the idea, and it tells it that it should free the whole array, not just that the element pointed to the pointer, because as you know, in this case psum is going to point to the first element of the pointer. So you want to use the delete. Okay, and this is the interesting thing, that you can do things like this for pointers, but you can't do this for array names, right? Because array names are not pointers. Okay, so pointers, arrays, and arithmetic. So let's talk about that. Okay, so let's finish this chapter now. So okay, so we know this. Okay, this is important. If you add one or decrease one, it increases the value by the number of bytes of the type where it points. What that means is, even if you add one, it's not going to increase it by 1 byte, but let's say it's a float, it is going to increase it by 4 bytes or something like that, right? That's the idea here. And we already spoke about that, pointer addition and subtraction. Here's the important thing, right? The address of an array. But wait, isn't the name of the array interpreted? Not quite. The name of the array is interpreted as the address of the first element of the array, while applying the address operator yields the address of the whole array. What does that mean here? So let's say this tel, which is an array of 10 variables of type short, and when you do tel, it displays this. But then when you do this, it displays the address of the whole array. That is what is most important, right? Normally these two, they are the same, but then when it is an array, it is different. So tel plus 1 adds 2 to the address value, whereas address of this adds 20 to the address value. And this is important because, as you can imagine, I'm just kind of jumping ahead here, but address of tel plus 1 adds 20 to the address value. What it means is, when you're multi-dimensional array, this is what you will see later as to the notation when you're going to jump from one row to another. So that's the idea here. And you can do something like this. Okay, we will look at that. Summarizing pointer points, this is important. Combinations of types, sure. Okay, just one small point here, since it's mentioned here. Just remember this: the structure. For a structure, you want to use something like this. That's the notation you want to use. You want to do, if this is a structure, this is pointing to a structure PPA, which probably it is. I kind of didn't look at it, but I'm pretty sure that's what it is. Yes. So as you can see, it's kind of pointing to ARP. Okay, and what is ARP? ARP is probably a structure defined somewhere, I guess. A structure pointer variable. Antarctica, years end, Antarctica trio, const. Yes. So here's the deal, right? Const is a pointer. Is a three element. Is the ARP is an array of 3 elements, and it has these 3 structures defined, and it's a pointer to that. So hence you want to do double pointer. It points to this guy, so you can do this. Okay, the vector class is similar to a string class. It's a dynamic array, and you kind of increase and decrease the size of the vector at runtime. It just manages that by itself. Okay, so you can do this. It's a template class. You can do vector int vi. It's a 0 size array of int, and then you can also say that, hey, create size of n double. So you can do either of these things. The array template can also do this. Similar to the vector template class, you also have an array template class, and similar to the built-in type, you can use this. Is fixed, uses the stack. And uses the stack instead of the free store. So this is important. It uses the stack instead of the free store. So instead of the heap, it uses the stack, and it shares efficiently and shares the efficiency of built-in arrays. So that's the difference between the array and the array template class, as to where the array value gets stored. And you'll see some other things as well. And this is important: comparing array vector objects and array objects. So what are the differences? Here's the interesting thing that at least I saw, which I found interesting. So here's the thing: A1 is an original C++ array, A2 is a vector, and you can do something similar to this. And array is an array template, and A3, and so is A4. You can do this. Okay, see, here's the thing: you can do something like this here, right? Array for array objects of the same size. You can't do that if that is an array. You can do that for array objects. You can't do that if it's an array. And you can do things like these. But you can also do something like this, which is kind of interesting. A1, you can do that, but it's advised not to, and hence it says that it moves backward by 2 double elements, putting there outside the array. C++ does not check, and what you want to do is, instead of doing something like this, it will allow you to do that, but it's not good. So you want to do an at, which will basically say that okay, index at that index. So you want to do something like that. Okay. Okay. And this is a summary. So as I promised, I just wanted to briefly end this lecture 4 by saying that this is what you should do if I were you. So look at this thinking. I know. So I think we all know about thinking in C, C++ books. So there is this thinking in C, beta, beta edition, flash lectures. And what is important about this is there are chapters. Let me see if I actually have that here. I think I have it on my machine. So let me just pull that up. Okay, so 1 second. Yeah, so what I would suggest is download this particular lectures, and what is very crucial, which I would suggest everybody to do, is look at these chapters. Okay, chapters 8A and 8B, and I think they are there here. Okay, yeah, so it's 8 here. Yeah, so sorry, chapter 7. First start with chapter 7, that is pointers 101. Just do that, and then look at, well, you can skip 8A if you already know Java, but then 8B, which is pointers 102. These are very good lectures. Okay, I think you absolutely should do that before you so that you, and I think the professor does a really very good job explaining pointers and arrays and everything about them, so that you just know what needs to be done. I think this is probably the best lecture I've ever seen on pointers. And let me see if I can. Okay, so it's probably trying to start the lecture, but I'm just going to talk about, okay, these are the various topics. For example, in pointers 101, pointers, try to start this. I'm going to say mute, but okay, so pointers. Okay, so let me just quickly go. If I can at least look at show the slides here, I think it will be helpful. Indirection. What are pointers? Pointer, indirection, address. This is an example. We know about this. The diagram, how do you think of a pointer? The address is stored and then it points to that variable. Reference semantics, simulating reference. Okay, so everything is passed by value, but when you do this, you can actually pass the address and it will think that it is passed by reference. Ragged arrays, you can do something like this. For int, argc and character, there's that how many arguments, what are the actual arguments. The null pointer, it doesn't point, you can't dereference null. Heap, okay, free c heap values. Examples, size of, we looked at that before. Structures on the heap. Okay, structs as arguments. Once again, structs usually pass that you want to do an address. So here is where you will pass a structure. You pass, you say it's a pointer and you pass an address to it. And when arrays are as arguments, you can do something like this. This basically means the same. Char pointer and char array mean the same. That's what's most important. And okay, some exercise. Now what? And let's just look at the return to index. Let's just look at the 8B slides as well, because once again I really like the slides, as you can imagine. Okay, I'm going to close this. Yes, pointers 102. Sorry. Oh, these are solutions. My bad. I want to go and look at the actual lecture and not the pointers. So yeah, as you can see, these lectures are 2 hours long total, and I'm just kind of going over the slides just for you to take a look at it. So this is what it covers. Unsigned. We just quickly talks about what is size t, unsigned keywords. Okay, and goes over that. Signed extension. This is important. The first bit stores the sign, whether it's plus or minus. So that's kind of important here. Take a look at this. Type def. You can type def something. Here what is type def is unsigned int is signed size t. That's what the type definition means. It's an alias. Think of it as an alias. and you can do type def structure foo as foo, so you can just do foo as, this is in C++ takes care of that by itself. Pointer to pointer, you can have whatever, so you can have star points to this, and pointer IP points to address of I. In this case, pointer IP7 and address. Here's the interesting thing: pointer in this is IPP. Sorry, when you say IPP, it, as you know, what you'll see is address contains IP and IP. So this contains 7, and address this contains this, which contains 7. Okay, so this contains kind of this. So IPP points to IP. That's the idea. You can, so it's two it's a two-level indirection. Arithmetic, we know about that. Pointers and arrays. So this is important. A is the same as A0, and you can do all sorts of these things. You can also do this, but don't do that. Are continued. What is size of A? Multi-dimensional arrays. This is what is important for multi-dimensional arrays. How will you do that? This is how you will write the syntax. So let's look at that quickly. So you don't have to, you can specify the columns, you don't have to worry about the rows. The compiler will figure that out for yourself, and then you define a pointer to an array of 4 ints. This is what you do, right? Int of 4, and this P is a pointer to an array of 4 ints, and then it points to A, and then you can do P plus, and then you can go around your business with P. That's the basic idea here. And yeah, so just look at this. I think this is really neat. Output, pointers and const. Okay, so what does this mean? The moment you do this const char pointer p1, you can't do this. You can't change what p is pointing to. But if you do it this way, you can do this, but you can't change the address of p. And if you do this, that you can now make any changes. These are some void pointers. You can, where it is useful for memcopy, doesn't really care what it is pointing to. It's just going to copy memory from one place to another. Pointers to functions is also interesting. Yeah, and here is where the auto in C++ shines a lot. Okay, functions and memory, incomplete types. Yeah, so I kind of gave you a quick whirlwind tour of pointers, but I hope I was able, I definitely recommend you listening these things and checking them out. Okay, thanks, bye.